So that should bring my screen in front. Okay, so we continue where we stopped before. So we have talked about what is the floating point unit on a processor and how it works to compute adding and multiplication and so on. Let's come to a more modern topic. So that is the so-called SIMD, or single instruction multiple data unit on a processor. You will see why that is important in a moment. So let's take a simple example. So you have an iterative multiplication. Let's say you have a loop and you have some data and you want to perform the same operation on multiple entries in an array, for example. So with an ordinary CPU, that would be like this. So we have 3 registers. The first 2 are carrying the operands, so the 2 factors for multiplication. And the third one carries the result. Like in this case, you have 9 times 3 is equals to 27. And now you go in memory through your array. So you have the input array, like with these numbers, 5, 9, 2, 8. And all of them are supposed to be multiplied by 3, right? So then you have the result also in memory would be 15, 27, and so on. So in order to do this for 4 elements, that would mean your CPU will have to execute 4 times a load statement or a load instruction to load data from the memory, 4 times a multiplication, and then 4 times a save statement. So to write the result back to memory. Okay. If you had a unit on the CPU, and that exists today, which is the SIMD unit, that could do this on a whole vector at once, that would of course be nice, because in this case that would look like here. So we have the SIMD unit, you have the input vector, which is then an array, in this case of 4 numbers. You have the factor, which is 3 in all 4 cases. And then you have the instruction to multiply, and then you would have the result vector, which would be then the full output vector, like 15, 27, and so on. Now, that would mean, if you count now the operations, that means you have one single load statement or load instruction to read data from the memory into the CPU. And that could, of course, read the full array, because in the memory, these numbers are next to each other. You just read one larger block, right, into this register. And then for the save statement, you have the same trick. So because you have an output array, you can save that output array into memory with only one instruction, namely saving a larger block. And also, in this case, for these SIMD units on the CPUs, the actual multiplication is just one instruction, because you have 4 parts in the registers, or you have long registers that carry, in this case, 4 numbers, and then you perform the multiplication in each of them simultaneously, right? So for this simple example, you see that all the operations are basically only 1/4 of the original layout of a simple CPU without an SIMD unit. Yeah. So therefore, we call this SIMD unit also vector unit on a processor. So that is, of course, very important. And the whole concept here we call vectorization. And the vector unit can efficiently work on such layouts of data. Yes, so modern CPUs even have larger SIMD units than shown here. So they go now up to 512 bits. And planning to be larger in future. That means you can compute even more numbers simultaneously. And also the SIMD units are usually directly connected to the cache on the CPU, which means if you read a larger block here, it might be fully available in the cache. And if you read the next block, it might also be fully available in the cache. And that means the loading and storage is very efficient in this case. Okay. So here's an example of the existing SIMD units, in this case for Intel CPUs. So what we had in the past, like maybe up to a few years ago, like 5 years ago, there was the SSE unit and the AVX 128 unit. These units were 128-bit wide. That would mean you fit either 4 times a single precision float, or you fit 2 times a double precision float, or you can fit, depending on which integer type you take, 16 times a byte, or and so on, yeah, or 2 times a 64-bit number. Okay, so that would mean this is what we had in common computers until recently. Now, today, we already have AVX 256 units in real CPUs that you can purchase right now. And they, of course, carry then the double amount. So you have either 8 times a float or 4 times a double, where you can perform your operations with one single instructions on 4 of them simultaneously. And the future CPUs, which will come out just in the next month and years, already have or are going to have 512 bits wide AVX unit. So that means basically vector calculation unit. And these units then, of course, carry 8 doubles, for example, or 16 floats. And that means, well, if you compile your code, there are actually commands where you can activate either, first of all, the vectorization itself. So in the Intel compiler, you have to actually activate that. And second, you can compile specifically for that type of processor that you own. Yeah, so depending on which of these units you have, you can generate code that exactly fits to this SAMD unit. So if it is larger, you make use of the larger unit, and instead of calculating only 2 doubles, you would maybe calculate 4 or 8 doubles at a time. Yeah, so that makes calculation very fast if you have a large array and want to perform the same instruction on it, like multiplication or whatever. Okay, are there any questions up to here? If not, then I will quickly explain what is a GPU, so a graphics processing unit. You see here on the left side a comparison to a regular CPU. So you have the control unit, you have the arithmetic logic units, sometimes 4 of them, and you have a large cache, which means you can provide a lot of data on the CPU for quick access. And yeah, maybe you have 4 cores, and so this would be a CPU with 4 cores, and that allows you, of course, to perform several tasks at the same time. And yes, so in this case, the performance of the CPU is usually good. So you have a low compute density, so only a fraction of the space is used for the actual computation. You have large cache sizes, and this is optimized for serial operations, like you have a few executions of the arithmetic logic units. You have high clock speeds, so these run at 3 gigahertz, for example, and usually you are not very tolerant to latencies. So if one of these units is operating and calculating something and the other units are waiting, then you lose efficiently very quickly. Yeah, so the efficiency is not good when only one of the cores is waiting or calculating. Newer CPUs have, of course, more parallelized cores, so that means you have 8 or 10 or 12 or even 24. Newest processors carry up to 64 cores. That means it is becoming more like a GPU slowly, and GPUs usually look like that. So you have very little space for the control unit and very little cache, but on the other hand, you have a lot of arithmetic logic units. So that means you have a high compute density. So most of the CPU is used for computations. The memory access is, of course, difficult because with little cache sizes, it means if you run out, so if the cache is not carrying the data that you need, you have to wait for loading from the memory, and that takes actually about maybe 1,000 times longer than loading from the cache. So that means you have a lot of wait time if you need to access large data. And so this is mainly built for parallel operations. So you have many parallel execution units. And the typical use case is a computer game where you can divide the screen in many parts and then calculate objects in 3D and calculate mirroring on objects, etc. So these GPUs, they have a high throughput. So it means you can do a lot of computations in the same time. And they have a high tolerance for latency. That means if one of these logic units is faster than the other, it doesn't really matter because you have so many of them. The average is running at good speed, you could say. Newer GPUs become more CPU-like, so they get additional functionality, which means the control logic needs to grow in a certain sense because they have more complex commands. So we have the tendency that GPUs become more or get more and more CPU features, and CPUs become more GPU-like. So, but still they are quite separate. I mean, you see it here from the plot. Okay, then let's talk about the actually memory alignment. What is that? And cache efficiency. So how to use a cache efficiently. So first of all, if you have an array, let's say here that is a 2D array, how is the alignment of this data looking in memory? So if it's 2D, you may have entries here A, B, C, D, E, F. And the coordinates or the indices of this two-dimensional array would be something like 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, and 3, 2, right? So that is your, how can I say, so that is the representation of the real data. But how does this look in memory? So in physical memory is a one-dimensional storage. Okay, so you have memory addresses that go from 1 to number n. And in physical memory, this array would actually look like as if you took all the lines and then connect them next to each other, like A, B, C, D, E, F would be a one-dimensional array. So now to use the cache efficiently would mean you want to access arrays in those directions where stuff is connected to each other, right? So if you access this array, let's say from A to B, then reading C and D, and then reading E and F, that makes it efficient. While if you would read A, C, E, and then B, D, E, F, that would mean you jump around in physical space in the memory. And that would mean you have to read this address, then this, then that, and so on. So you would be jumping back and forth in the physical memory. And if you have a 3D array, it makes it even worse because then it is much more scattered. So let's say you have a 3D volume, and what we do in the Pencil code is to improve or to actually use the alignment of the data in the memory. We usually have one dimension, which is in our case the X dimension, where the access is aligned. Yes, so all that data that is in this cube is aligned along these bluish elongated domains, yeah, where each of them is one coordinate, so to say. Yeah, so that would mean if you read a full such array, you would be reading here, for example, the blue ones or the green ones or the yellow ones. That would be efficient because that is our fastest dimension. And reading into the cache means if you access, for example, the value here at this spot, the cache has a given size. So the CPU always loads the full block into the cache. Yes, so if you have a cache size of whatever, it would read not only that address because it costs the same amount of time to load the full block into the cache, it would read always the full block. And if you then jump to the next coordinate and need the value here, then very simply, it is already in the cache. You don't have to wait for the memory chip. You can directly access it from the CPU, and that makes it fast, right? So as long as you use the data along the alignment of the data in the memory, you are automatically using also the cache efficiently, right? I hope that everyone understands that. And if not, please ask now, because you can ask anytime and interrupt me. So once we have been working along the fastest dimension, what do? Well, next we go along the next slower dimension, which in this case would be here the Y direction in Fortran. So after reading through here, we would connect to the next such elongated structure. And that, by the way, is what gives the pencil code the name, because this you could see as a stack of pencils, right? In 3D, that would mean the pencils are oriented along the X direction. Then next step, you would read along the Y direction. That means you go the stack up here. And then after that, reading the second pencil, reading through all the pencils along the Y direction. What you would do then next is you go along the slowest direction in 3D here. That would mean the Z direction. So this is here going into the plane. And with these elongated subdomains and reading in this order, you automatically have an optimal access to the physical memory, to the data that is stored in physical memory, and you have an optimal use of the cache. So that is why pencil code is designed like it is. So why we use always a full pencil. So full pencil is means it carries always all the values, all the quantities along the current x or all x coordinates along the current y and z that we calculate. And also we carry in the pencil code pre-calculated so-called
Naveen has a question.
Yes, please.
Naveen, can you unmute and ask? Naveen is not able to unmute or not.
Okay, we can, yeah.
Hello.
Okay. Yes,
yeah,
please.
My question was, you are like storing the whole X array in the cache, right? Let's say if we don't have that much of length in the X, which can fill the whole cache, then what of the rest of the space in the cache will happen? Will you fill it with some other X?
Yes, very good question. So if you had a 2D array and 2 elements is not enough for the cache, what it would do is it reads the full block, which would mean it would connect to the next line in this 2D array. Yeah. So if the cache is this size, so 4 elements, then it would read A, B, C, and D. That means if you go along the Y coordinate, then in the next iteration of the next loop, in the Y loop, so to say, it is already there. Yeah, and that is why it is important to go first along the fastest direction, then iterate along the next slower dimension, which is in 3D would be Y in pencil code, and then in the Z direction, because this aligns then in memory, in physical memory. Does this answer your question?
No. What I meant was like, if you could not, let's say if your X, let's say other way around, if your X is in X direction, you have a lot more data, you cannot fully fit all into the cache.
Yes. Okay, that's also a good question. So what would happen then is you first fill whatever fits into the cache, and then, and honestly, the cache carries at least 1,000 elements. Okay, so that's large. And if that is not sufficient, and the first time you want to access a data that is outside of the cache region, it would automatically read the next block from the memory into the cache. Yeah, that's what the CPU does that automatically. So that would mean first you use the first 1,000 elements. Then if you go beyond that, it would read the next 1,000 elements, and so on and so on. Okay? Good. And yes, and what we do have in pencil code is these so-called pencils. They carry pre-calculated quantities in the same orientation, so in the shape of these pencils, or elongated subdomains here. And all important quantities do exist pre-calculated. Of course, each module has to register the pencils that it wants, that it requires. And that would be, for example, B2 means the magnetic field squared, right? So that is a scalar. And for example, there could be, and all of them are called with P% and then the name. For example, P% LNTT would mean you have the logarithm of the temperature pre-calculated and in the full extent along the X direction in one array. Yes. And then you iterate, of course, in the pencil code, or the pencil code itself, it iterates through through Y and Z, and always covering the full X dimension to make it efficient in the computations. Okay, are there more questions?
So is this what was a cache miss? I mean, the question that Naveen was asking, that you have the cache size is less than the size of your X.
Yes, no, a cache miss is what we say when required data is not in the cache, when it requires reloading the data. What Naveen mentions is a regular access. So you first fill the cache, work it through, and then you fill the next block with the into the cache. So that is regular behavior. What is a cache miss is when you load the full block and use the first element, and then in the next iteration, it would have to load another block, not covering the full entry of the cache, but only accessing 1, 2 elements, and then it would have to read another block because you're not accessing the array in the right order. Yes,
I see.
That would be a cache miss, and that would be very inefficient.
So suppose the loops are not, so suppose I switch the loops, then I would have more of cache misses.
Yeah, right, exactly. Yes, that is what would happen, right? Yeah. Except if all the data fits into the cache, but that is unusual, that you only have 1000 points. So yeah, in total, I mean. Yes, okay. So here's an example of how to do it correct and how not. So that could be read and could be write, whatever. So for example, we have the same 2-dimensional array, and we want to write something in it, like the number of the element, like we write 1, 2, 3, 4, 5, 6 in it, right? So let's consider we have a for loop, and then we iterate in the y direction from 1 to 3, and then we iterate in the x direction from 1 to 2, and then into f index ix comma iy, we write the actual number. So that would be ix plus iy times 2 minus 2. So that would be a numbering like 1, 2, 3, 4, 5, 6. Okay, so in C, C++, and in NumPy, so in Python, this would be the typical order to use this array, right? This is what we call so-called row major ordering of arrays. While if you have Fortran, IDL, Julia, MATLAB, and R, there you have so-called column major accessing of arrays. That means in the one language, the data is aligned first along Y and then along X. In the other language, it is aligned first along X and then along Y, okay? So in these two cases, when we have these two loops, we are actually reading and writing from it in a certain order. And that would mean if we write it out one-dimensionally, these two are equivalent examples because the loop here is switched. Yes, so we have in Fortran case, we have ix outside and iy inside. Here it is switched. That would mean we write into this array in the order as you see the color. So we first write the 1, then we write the 3, then we write the 5, and then we write 2, 4, and 6 into the array. And that would be exactly not what you want, right? So that is what we call unaligned access. So we write in the array in the wrong order. So instead, what you can do is aligned access. And again, example for row major and column major languages would be to switch the loops so that the accessing of the array is in the right order. So we first write the 1, then the 2, then the 3, and so on, in exactly the way how the data is stored in memory. Yes. So if you have Fortran 2-dimensional arrays, you would have the outside loop would be Y and the inside loop would be X. Yes. And for C, C++, and Python, it would be exactly opposite. So the inside loop would be Y and the outside loop would be X, because they do represent the data physically different in the memory. Yes. So for you, important to know if you use Fortran and IDL, you have to follow column major. That means the innermost iteration is always along X, and then you are efficient. Okay, is that clear? I hope so. Good. So that makes the sunshine, right? Good. Okay, let's finish a bit on this topic, vectorization and the SIMD unit. So just if you have a longer iteration on many elements, for example, you would iterate, or you want to perform it in an operation, like here in this case, we take to the power of 1/4. Yeah, so you take the element A11, yeah, perform the operation, and then you iterate, right? And then you iterate over the elements A, B, C, D, F, and so on. So for a regular CPU, that means you have 6 times, you have to execute the actual loop for the iteration. So you have the loop overhead 6 times. Then you have up to, depends, 6 times to load data from the memory, you have six times the actual mathematical operation, and then you have 6 times storage instruction to execute, to write the result back. On an SIMD unit, on the other hand, as you understood probably already, yeah, you have the full array on the CPU. You have the same instruction with the same operand, but multiple data. And you have no loop overhead because there is no iteration. You do it at once. You have one memory load. So that means, depends on your cache. If you have if you have it full in the L2 cache on the CPU, that would be very fast. You have one mathematics operation and you have one store. And that makes this case, if you have large arrays, up to 1,000 times faster. Namely, so many times how many data fits into the cache line, like in the L2 cache, for example. And that is usually 1,000 elements. So, and the iteration of the SIMD unit on top of the cache, that is extremely fast. So that is very well optimized because it's really on the same physical chip. And that goes very quickly then. Okay, so that makes it very efficient. So if you have aligned access and you use the SIMD unit and everything is vectorized nicely, then the computation is really fast, optimal, I would say. Of course, there's always a kind of dilemma. You can spend a bit memory to save instructions or cycles on the CPU, as we say. I have some code example that I could show later, but I just want to mention maybe if you compute something from a large array, it could be that if you have a certain part of an image that you want to compare with other parts of the image, that you first create a set of parts of images, even though it uses much more memory than if you have only the image itself and then copy a part of it each time in each operation, in each iteration. You could prepare a set of prepared samples or prepared cutouts of an image and then perform an operation on it. Yeah, because then you have aligned memory and you perform the operations along this aligned memory, and that makes it efficient. Instead, if you would read a part of an image and another part of an image, which is the same data physically, the same array, and then compare them with some operation, and then read a different part of the image and a different, compare that with a different part of the same image, that creates cache misses, right? Because you're not, maybe not always reading the neighbors, but if you prepare all the data in advance, even spending some memory, you could in the end run faster because that data is pre-aligned, right? So that makes it possible to do optimization on code, sometimes spending memory and gaining speed. And also the other way around. Sometimes you had maybe an idea for an algorithm that runs very fast if you spend this and that amount of memory, but you can't because it's not available. Then you have to spend more instructions and saving memory. Yes, and then there's one topic maybe that is still, last topic, abuse of mathematics. That is a nice topic. Well, you can look at this curve here. This is a cosine function. It's basically a step function as we have it in the pencil code. If you want to switch something off, let's say with time or on, whatever, you use a step function, which makes a smooth transition. Instead of a hard step, like a Heaviside function, you use, for example, a cosine. Now, look at this plot. This is another function. Did anyone spot the difference? So if I switch between this and between the other one, you see there's only tiny differences. But what is this function then? Well, this function is what we have here. It is the so-called cubic step function as we have it in the pencil code. And basically saying this is a cubic polynomial, right? It's nothing special, but it looks very much like a cosine. And it has even advantages. First of all, the number of computations are less. A cosine takes a lot of multiplications, additions, powers, etc. So exponents. That takes a lot more time than computing a simple third order polynomial, right? But the third order polynomial does the job very well. And in particular, it has zero derivatives at the boundaries here, which is of course nice. And if you regroup that polynomial in this sense, as you see it here, you can even save more computations, because if you do these computations here with, in this case, with the new coordinate here, xi, then you have maybe xi squared, and you have one addition or subtraction. It's the same operation, just with a different sign, and multiply that once with xi, and then add another 1/2 here. That gives you the full polynomial, but you have saved some multiplications, because if you write out the polynomial with all of the orders, like psi and psi squared and psi to the power of 3, then you have 3 multiplications, and in this case you have only 2 multiplications. And that, of course, makes it even more efficient. That is a way how you can abuse mathematics, so to say, in order to get more optimal code, like approximations of functions. Yes, maybe I should quickly go, if I can, we have another 5 minutes maybe. I could go through this, how to scale a code to more than 8,000 or 10,000 processors roughly. Well, this is a scaling plot from the pencil code. As when I started my PhD, so that was about 2009 or so, or 2010, where I did test runs. And what you see is if you use more and more processors, so that is the number of cores here on the horizontal axis, the computing time, of course, goes down, but then all of a sudden it goes up again, right? And that is different for different hardware. Like if you look here, this plot, yeah, you could use 1024 cores efficiently, but then the computing time goes up. So if you use more processors, it takes actually longer than if you take less processors. So that looks funny. What is the difference between the two CPUs? Not only is the red one that scales worse, faster, it's running 3 gigahertz, but it has a smaller L2 cache. Yeah? So here you now see the power of the L2 cache and the vectorization. So that means the second machine, even though it is running at lower speed, is actually computing more iterations efficiently. Yes, because of the larger cache size. But also what you should see is there's always an optimal number of processors. If you make the subdomain too small, yes, then the X dimension is too small to fit into the, or is actually not filling the cache or not filling the vectorization unit. And then you don't run efficiently because the vectorization unit has nothing to do, right? Because it's only having small cache lines, and that runs maybe 64 is maybe a good number that you should have at least along the X direction, so it's 64 points. Then it might be running efficiently, but if you had 128 points along X, that makes it, of course, more efficient. Okay, so yes, major steps in the scaling. So first you have to run reliably on one core, right? That is to create autotest data. So you have a test set. You know what the output should be in the full 3D volume, which means, yeah, everything computed on one core. And then you can start comparing when you use multiple cores. Let's say in this case, we use 10 cores. Then you could do a parallelization along 1 or 2 coordinate directions. So you could, in this case, you could parallelize along the Z direction. So you have multiple processes along Z, but the full extent along X, which is of course nice. Then it is nicely aligned, and the iteration is fast. If you had, let's say, 100 cores, then you could do parallelization with about 4 cores or more per coordinate direction. So you could start also parallelizing or dividing the setup in the X direction, which is, of course, you'd want to avoid usually because the X direction is fast. So you want to have it as large as possible. But if the subdomains are too elongated, then the surface volume ratio is not good. And then there's too much communication between the processor boundaries because they need to communicate the values at the boundaries, each iteration. And if you then do parallelization with 100 cores only in one direction, then this is most probably not efficient. So you can start parallelizing along each direction. And still, of course, the output must be identical to the autotest data. So if you had some mistake in the parallelization, you would then see it. If you go to 2000 cores, then you have to start thinking about your IO scheme. So how you save the files. writing with 1,000 processors on a storage system, no matter how capable it is starting to become a pain. Yeah, because if you have 1,000 processors that want to open new files at the same time on the same storage system, it definitely has not 1,000 hard disks, it has less. So then there will be a clash. Something will be clashing somewhere, right? So you may be blocking one IO with the other one. So first, that is what you have to think of. Second, you should optimize all global communication. So if you have 1,000 processors and a value needs to be communicated globally, that makes it slow because you have one processor and that processor has to send it to all the other processors. And that, of course, takes time. And furthermore, if you have such large setups, you want to avoid all types of global arrays. Of course, if the array is only, let's say, the coordinates, so the x coordinates, for example, or the z coordinates, that might still be okay because it's one-dimensional. But with these large setups, having a global array, like a three-dimensional global array of everything, that kills you. So that would mean you could not fill it, or you could not, the RAM of the computer could not host the global array even. Once you start talking about, let's say, 8,000 processors or more, then you will really have to find the weak parts in, for example, especially in the boundary conditions, because remember, the boundary conditions are applied only at the boundaries. That means only specific processors are working at the boundaries to compute the boundary condition, and the rest of the processors that are in the interior, they have nothing to do, right? So if one boundary condition is hard to compute and takes a long time, then maybe 95% of your processors are just waiting. And that is, of course, not good. So you want to optimize really the boundary conditions so that the computation is fast and most possibly parallel. Second, you want to divide your volume into subsections. So maybe if you write the data, for example, you could collect all the data along X and Y, and then have specific input-output processors that write the whole slice at once in one file, right? And then in the next slice of code of the volume, you would again communicate everything along X and Y, collect it, and then write it out into a separate file. So that would mean you wouldn't write 10,000 files, but you would write maybe only 100 files, right? And the data would be combined already. And a final point, of course, you want to avoid also all global communication. So global communication with 10,000 CPUs is really harmful. Okay, that brings us maybe to the last slide. I can skip that. I think I explained it already. So the volume surface ratio is, of course, better if you have cubic domains. But if you have elongated domains, you may better fill the vectorization unit. So there's always some optimum in between. And for the Fourier transform, for example, we have currently a scheme where if you had cubic subdomains, it needs to transfer actually in elongated subdomains, because Fourier transform requires the data, all the data along X of the whole volume, or along the direction where you transform, right? And that is actually done efficiently. Also, the writing out of the data is done. We have IO modules. Johannes will tell in one of his presentations about the IO schemes. And what you can see then is the new scaling plot here that I made in, I think, 2013 or 14. That was after my optimizations of the same setup, right? So now if you overplot the old scaling plot to the new scaling plot, you clearly see the difference, hopefully, right? So up to here, we are almost identical, but then you see after the optimizations on the same machine, by the way, we had a better scaling, so we could use even 2,000 or 4,000 processors efficiently on, and that was a 1,024 cubed model. And yes, and by the way, so the symbols is cubic subdomains and pencil-shaped subdomains. So you see cubic is a bit behind, of course, but not so much, so it's still usable. Okay, good. I think that's the end of my talk. So are there any questions?
Let me see if there are any raised hands. So here, what did you exactly do? I mean, to change. So it was not in the code. It was basically how you distribute the domain into processors, or
first. Second, it was in the code. So I managed to do the Fourier transform in parallel, which was originally not in parallel. It was performed on one processor and then distributed the data. Yes. So that would mean you have cubic subdomains for efficiency, and then you transform, that's a kind of bookkeeping with the indices. You transform the data into pencil shape, compute the Fourier transform, and then you transform back. And that was actually done on the boundary condition. Yeah, so that is coming back to this ideas that I list here. We were optimizing the boundary condition. We were improving the parallelization of certain functions like the Fourier transforms, and following all these steps. So avoiding global communication, avoiding global arrays, and optimize the code, of course, where possible. Yes, introducing new pencil quantities that helped a bit. And all these steps together then allowed me to run even faster than before. And that the most important contribution here was due to the boundary condition. So working on the Fourier transforms.
Oh, and one question is that when you are doing this benchmarking in such large number of processors, cores, a problem that we face is when we submit the job, we're always getting a different set of CPUs, right? And then that changes the
performance.
Yeah. So how do you tackle that? How do you make sure that it is not the processor?
Yes, I don't run 1 hour. I run 10 minutes because it's still good enough to have quite precise measurements.
Even for 10 minutes, when you submit a job, you have to. So do you specifically ask for a particular set of nodes?
No, I didn't. What I did is I ran multiple times.
So the same setup with the same configuration multiple times.
Yes, and then you see, you will hopefully find the outliers of the distribution of the data points. Yeah, so you can either do the mean. This is what I did. I compute the mean. You could do the median. You could do the minimum, for example. But the minimum is of course not applicable. Yeah, because in reality, when you run in reality, you get the mean. Yeah, sometimes you have a good distribution, sometimes you have a bad distributions. That actually depends on which nodes you have on the network. How far are they apart from each other? Are they connected through only one switch, or are they connected through multiple switches? That takes, of course, more time to communicate. And if the node setup is not optimal, this is the usual case. So what I did, I run, for example, 10 times, and I take the mean of the run times. And then the outliers are hopefully not so important.
Okay. I'll ask one question.
Shohil has a question.
Yeah. So Phillippe, you mentioned about this SI in the single instruction multiple data thing. So I have seen that people use this Intel flags like Xhost or AVX512 or AVX, so AVX Xcode thing. Even I have seen some flags like heap arrays. So some of my friends are saying that heap arrays actually helped them a lot for executing large jobs. Even they become faster a bit. So what is your take on this? So do you suggest that at every time we should use this Xhost or AVX512 like flags and heap arrays?
I can show you what my suggestion is. So it is checked in, of course. So here you see the config directory in pencil code.
Right.
Do you use PC build or do you use the make command?
Make.
Okay, then you can simply look it up and adapt for you. So we have here, in here we have the compilers directory. And there's, for example, the Intel compiler standard configuration is this one. I can just open it quickly. So you see it includes the separate configuration for Intel iFort and Intel C compiler. And then in addition, I have this directory extensions. Yeah. And then, for example, for Intel, we have the debug extension, which is debug options. We have the optimal extension, which is for optimizing the code for production. And the same we have also for the GNU compiler, for example. Yeah.
Okay.
So I can open it too. Look, for example, here the Intel compiler. For the Intel compiler, there we use O2 for the optimization flag first. So that is the maximum you can use if you want to have accurate mathematics. Then next, what we do is the so-called interprocedural optimizations, single and multi-file. This is the IP and IPO options. These are strongly recommended because this allows you to do vectorization also between calls of different functions between different modules. And then the most important flag is xhost, which means we optimize the code for that machine where we are compiling. Right? So on some supercomputers, or in most supercomputers, the login front end where you log in have the same CPU type as the compute nodes.
Right.
But of course, there are exceptions. And then the computing center will have to tell you which options you should set. So there should be a documentation and you can look it up, and maybe it is some other name, like if it is an AVX unit, it is named X AVX2 or something.
Right.
But the usual case is this one. That should work in 95% of the cases, I hope. And for the GNU compiler, we have this one. It is called mark equals native. And that also means the CPU where we compile is the CPU type that we optimize for. And the O3 flag in GNU is actually the same as the O2 flag in Intel. It's written here. So if you want to see it, you can actually read the comment here.
We always use the O2 flag.
Yes, for Intel, O2 is maximum, yes. I mean, unless you are not interested in accurate mathematics, but I guess not. Okay, yes. Then, I mean, if you have a particularly large setup with Intel, we have this one, Intel_large. And there you see what we do is MC model equals large. That is added to the set of flags.
So this
otherwise,
is a large number of processors, or if your problem size is large?
That means large amount of memory.
Okay.
So if you have a 4096 cubed, you will have to use this option.
Yeah, otherwise it won't compile.
Yes, it will. Maybe it will compile, but it wouldn't run.
No, on some machines it doesn't even compile.
Yes, yes. On Cray machines it doesn't even compile. Right. So if you want to look up for Cray, the extensions are also available. So Cray Optimal I have here. Cray Optimal. There we have this flag and this flag. There is no Cray compilers. I think maybe they have it already turned on automatically. I'm not sure.
Yeah. Okay. Jon has his hand raised. Maybe he has a comment or question.
Yeah, just maybe 2 comments. So one comment is, of course, that for the new users, I mean, what Philip showed is very nice, the scaling, but I think we can all show off a bit more. I think nowadays the scaling even goes to 20,000 or 100,000 cores. So it scales, actually pencil code scales pretty well, depending on of course on your problem, but in general it scales very well. And my experience is as well as Philip said, so using processor distribution for large ones which are isotropic, so cubic, is turned out to be actually quite the best. And maybe one comment to what Piali said about the different nodes and stuff. So there are certain flags you can put in your submission script. For example, I think I talked about it last year or the year before.
Would you like to show it?
This M-plane. And so that makes sure that you only get certain nodes which would work very well. So there are certain flags you can use, and they make a big difference.
This is
can be a factor of 1.5.
The job submission.
Job submission. Okay. You're talking about the job submission script, right?
Yeah. So, for example, if you use SBatch or something, there are certain commands which helps a lot.
So if you want, you can show it actually. I stopped sharing, and I think that's the end for my lecture.
Jon, for this 90,000 course, what kind of sample? I mean, is it a standard sample in the pencil code that has been used, or is it some specialized setup that you have for this scaling test on 90,000 processors, you said?
Yeah, I don't know what, I think I did recent, I mean, I share now first the one thing. Let's see. So this is a submission script. So that's a run with 18,000 cores, for example. They have something called -m plane 40. So because it's like this, that every node has just 40 cores. I don't know if you can read it. It's maybe
yeah, be able to see it.
So there are certain things like this, and this makes very a difference if you do the big runs.
I see. Okay.
And
so how do you find these? Are you to talk to the engineers on that?
Script manuals.
I think, yeah. So that's so there are certain ways where you can even optimize a bit more, and you see, and there's sometimes even that you can select different nodes, you know, that you don't get. I mean, it's true that if you get like a distribution of processors which are very different, that is not so good. But I think there are certain flags you can use to select certain types or something, or maybe the computer center can arrange something like this. Like we said, I only use the newest processor, or I just want to have the older one, or whatever. So that you have to maybe discuss with the computer center.
Well, I could say in a good computing center, you wouldn't have to do that because someone takes care of it.
But they are not usually. That's true. Okay, so let me see if there are any more hands. Yeah, I don't see. So yeah, thanks all of you, especially Philip and Naveen, for your lectures, and I hope you will be able to upload them to the Slack channel. And we have recorded it, so now let me just stop.